Let's take a look then. We're going to do more of our chapter 5. Hey, Mike. Thanks, Mike. We're leaving. We'll see you later. You guys are leaving? Have a great day. Thank you so much, brother. Thank you very much. Okay, so let's take a look. So in the lecture from yesterday, got posted very late. Sorry. We covered like an introduction to energy, right? And I looked at the difference between kinetic and potential energy. And then we covered the gas cylinder problem. The gas cylinder problem is like, it's a word problem, so it's challenging because you have to interpret the meaning of each word of the sentence and all of that. And there's all these rules and stuff. So that one's a little tricky. So we're gonna we'll come back to that a little bit later. But I want to show you a little bit more about what's called pressure volume work, because the pressure volume work is referring to the mechanical work that we used in that calculation with the gas cylinder problem. So let's take a look here. So calculating pressure volume work. A mixture of krypton and oxygen gas is compressed from a volume of 87.0 liters to a volume of 72.0 liters, while the pressure is held constant at 64.0 atmospheres. Calculate the work done on the gas mixture, and then round your answer to 3 significant digits and be sure that's the correct sign. So the sign is, in a sense, the sign is the most important thing when you do these sorts of problems. And an analogy would be money. So if you were counting money coming in and money going out, and at the end of the day you said, hey, we took in $1,000 more money than we gave out, your profit's $1,000. But in fact, you gave out $1,000 more than you brought in, so your profit was negative $1,000, right? That's a big difference, right? So getting, 840 versus 860 is not as important as positive 800 versus negative 800. You just say, hey, the sign is the only thing that's wrong, but the sign is actually what's important. Right? We want to know whether energy is coming out or going in. That's what the sign is telling us. So this is called pressure volume work. PV work is usually what people call it. PV work, pressure volume. And the idea is this. If you have gases that are inside of the cylinder and you're pushing down, this is called an external pressure. External meaning from the outside. Okay. There's energy associated with either compressing the gases or the gases pushing upward and expanding. So you can either get expansion Expansion means that the volume is larger than it was. So now the gases are over here. And there's energy associated with that process. Right? In a way, here's an analogy. It's kind of sort of like this. If I have this eraser and it weighs, let's say this weighs like a couple pounds, it takes energy to push it up, right? Because gravity is pulling it down. So there's energy differences as it moves from one position to another, one height to another. The same is true here. You can think of this external pressure as pushing down the gases. So if the gases are able to push the external pressure upward, there's energy associated with that, energy transfer. Okay? And we call that work, WORK. But it's also the case that if this external pressure is able to compress the gases to make them occupy a smaller volume, there's also, this is called compression. There's also energy transfer associated with that. There's also work associated with that. The only issue is, how do we differentiate in terms of work between this process and this process? And it's just the sign. whether it's positive or negative. If it expands, the sign is negative. If it compresses, the sign is positive. Okay? So in this case, W is positive, and in this case, W is negative. That's the only difference right there. Okay? Does that make sense? But it depends whether you're talking about the gas or the surroundings, right? So we're going to look at, when you do these calculations, we're going to look at it from the perspective of the gases. So that sign convention is from the perspective of the gases. So, if it says that, it's doing work on the gases, that's good. If it says that it's doing work on the surroundings, that's the opposite. So that's a good point. Okay. So before we do the calculation, there's a little hint here. It actually says work was done on the gas mixture. That's actually telling you what's being done on it. So if it's being done on it, that means that the gases are gaining energy. If work is done on you, that means you gain energy. If you do work on something else, that means you're giving it energy. So they're kind of giving you a little hint here to say that, in fact, the gases are absorbing the energy, so it's going to be positive. Okay. Now you can also tell what happened to volume. See how it got smaller? So it started at 87 and went down to 72. If it got smaller, that's compression, right? So if it's compression, it should be positive. Okay. And in fact, that's essentially how the internal combustion engine works. Is that what you do is you have a cylinder, right? And you have air, which has oxygen, and you have vaporized gasoline, vaporized fuel. So you have a gas mixture, and then there's a little cylinder, a little disc, a piston, that pushes down on it, compresses it. As it gets compressed, it has more energy. And then it's ignited, and it gets really hot in there, and that pushes the piston back out. So it's that temperature change. We'll talk about that when we get to gases in chapter 10. But the increase in temperature tends to make gases expand. And so it does work on the piston. So it expands and it's doing work. So where's that energy going? It's going out of the gases and it's going into the piston. Now the piston is then connected to a bunch of mechanical devices that allow rotation motion, and now you can move your vehicle. Okay. Now, the issue here is that how do we do this calculation? Saying calculate the work that's being done on a mixture, right? So how do we calculate work? For this particular problem, the calculation is very simple. Work is minus the external pressure, so I'll write EX for external, times the change in volume. And I'm not going to derive that in here. There are derivations available. Actually, maybe I'll make a video of that just if people are curious. Most people don't really care that much to see the derivation. But there's a relatively simple derivation. It's in mostly it's in physics books. But what this says is the amount of work is equal to the negative of the external pressure. So our external pressure has to be given, right? It also has to be constant. If the external pressure changes, you can't use that equation. You have to use a different equation. There is an equation you can use, but we're not going to do it here. Okay. So that number is going to be given, and then you just have to find out what delta V is. And that delta V is just V final or V2. I'll use number as subscripts. V2 minus V1. So your final volume minus your initial volume. Don't forget the negative. The negative is there to ensure that compression is positive and that expansion is negative. That's why it's in there. Okay. Any questions so far? Make sense? The formula is actually pretty simple, right? It's just, the issue here is the units, so I'm going to talk a little bit about the units as well. But let me go ahead and I'm just going to run through the calculation. So we'll calculate W using these numbers, and then we'll go through the units. put that up here. W is minus P equals minus P external times W. All right, well, we've got, we've kind of got all these numbers, right? So we have 64 atmospheres. So negative 64 atmospheres. It looks like it's 64.0. So there's your external pressure. And then we have to do V final minus V initial. So it goes from 87 down to 72. So V2 minus V1. Okay. So it's 72 minus 87. Okay. That's a minus. So V2 minus V1. Okay, so that's minus 15, right? So really what you have is minus 64 atmospheres times minus 15.0 liters. So that's 649.60. Now, what's the sign going to be? You have a negative times a negative. So that's a positive. And then the units are going to be atmospheres times liters. And so that would be the amount of work, but here's an issue. By the way, that is positive, so that tells us it's compression. So that means the gases have more energy at the end than they had at the beginning. They gained that much energy by compressing them. These are strange units for energy. For energy, our units are typically joules or kilojoules. If you're doing food chemistry, you might say calories or kilocalories. There's some older units called hertz, but these are very strange units. So Alex, in this particular problem, they don't tell you what they want the units to be in, but the units are, you probably want, well, actually, they may actually put in the little, they might put kJ at the side or J at the side. So let's do the conversion. The conversion is 1 atmosphere liter is equal to 101.3 joules. And that's the conversion between atmosphere liters and joules. Okay? So typically you want to have them either in joules or kilojoules. This is going to be a pretty big number. So most likely you want to have it in kilojoules. So we'll do that next. So we'll start off with this and then use this as a unit conversion. 960 atmosphere liters times, now we want to convert it to joules, so we're going to put this in the numerator. And then we'll put this in the denominator. Okay. And then your atmospheres cancel, your liters cancel, and you got joules. Okay. So 960 times 101.3, and it looks like it's around 97,000. So I'll write down 97,200. Okay. Put a decimal point there, yes. But like I said, typically when you have thousands or tens of thousands, you convert it to kilojoules. So one more conversion, which would be a kilojoule is 1,000 joules. Okay, so we take our 97,200 and then convert it to kilojoules. Now, all you're really going to do is you're just going to move the decimal point 3 places. So you get 97.2 kilojoules. Okay, so that is how much more energy the gases have at the end of this process than they had at the beginning. Right? So chemicals have energy, right? So our bodies have energy. If you take in food, you have more energy now, right? And so same thing here. By taking these gases and compressing them, doing mechanical work on them, they now have more energy by this amount. That's how much more energy the gas will produce. Okay. And then that energy could be used to do something. It could be used to produce heat. It could be used to do mechanical work in the future, but it's in there in this gas. These gases have that energy. Okay. Any questions on that? Make sense? The main tricky one there is that they don't give you the units that you need to actually get the right answer, right? And let me make one little point about this number. This is the number that Alex wants you to use is a little different than this one. It's not exactly 101.3, but it's in their table. So if you look up their table of constants, you'll find it in there. It's like 101.3 something or 101.2 something. It's pretty close to that. All right, so there's that's called pressure volume. And this pressure volume curve is important because what we said yesterday in the lecture was that when you're talking about a system of gases, you can figure out how much energy the gases gain or lose using this equation. So gases, so just consider this like their total energy of the gases. That's what E is. E is total energy that they have. Now, when you're talking about gases are in motion, they're moving around, they're bouncing around, so they have energy. But this is saying, hey, imagine they have energy, and then you give them some energy. They have more energy. Or you take some energy out, now they have less energy. This delta E is telling you how much they're gaining or losing. So they can either gain or lose energy through heat or through work. So this one right here, that's what we just calculated. Right? That gives us the equation for that one right there. So in this section, when we get to the next section on calorimetry, we're going to look at the equation for this one, the one that will tell us that. And then that will give us, both equations to be able to calculate. Yes, let's get to this one here. Now we're going to look at something called enthalpy. So understanding the definition of enthalpy. So let me give you the definition of enthalpy, at least the mathematical one, and then we'll work from there. So enthalpy, the symbol for enthalpy is H. So that's the symbol for enthalpy. I use it, I kind of remember it this way. Think of enthalpy as heat. So we're going to use the symbol H for heat. So there's a relationship between enthalpy and heat that we'll look at. And then there's something called delta H, which is called the change in enthalpy. And that is equal to H final, or H2, minus H initial, which is H1. So this is enthalpy, that's the symbol for it. And then this is the difference in enthalpy. So imagine something has a certain amount of enthalpy, a certain amount of energy, and now it has more. Delta H would be the amount that you added. It's just the difference between what you started out and what you ended. So it's analogous to delta E, right? Delta E is how much you start with, and the difference between how much you start with and how much you end with. Okay, so we'll see a lot of that, of changes. Now, what is enthalpy? Let me give you a little equation for it. H can be written this way as the total energy plus PV. P times V, pressure times volume. So that's a definition of enthalpy. It's the amount of internal energy, the total energy of the gases, plus whatever the pressure of the gases is times the volume of the gas. Okay? Now, we're generally more interested in this than we are in this. Okay? In fact, it's very rare that we look at H. We normally want to look at L because we want to know how much energy went in or came out.
Wait, could you just go over what you were again?
So E is the total energy, so how much energy do the gases have? And then P is the pressure of the gases and V is the volume. So imagine a little container. So all these gases are in here. There's your gas mixture. Let's do it this way. Imagine I have external pressure. Okay, so I'm pushing down on these gases, and this piston is not moving, it's stationary. If it's stationary, that means the pressure on the inside is equal to the pressure on the outside. Because if the pressure was larger in here, it would push it up. If the pressure was larger out here, it would come back down. So that means these two, this is not moving. So that means those two pressures are equal to each other. So you could say, look, I'm going to measure this, and that will tell me what that is. So that's the pressure on the inside. The volume is just how much space it takes up. That's easy to measure, right? So interestingly enough, pressure times volume is actually an energy term, right? These are all energies. This is energy, this is energy. If this adds to that, and this one's energy, that means this has to be energy too, right? You can't take a force and add it to an energy. You can't take a length and add it to an area. You can't take time and add it to mass. You can multiply them, divide them, but you can't add them. So that means that if these are additive, and this one's an energy, that means this has to be an energy too. So anytime you have a collection of gas molecules, you have energy. There's energy in those gases. So if you have a balloon has a volume, a balloon has a pressure inside, right? You can kind of feel the pressure. Push on the balloon, it pushes back, right? You're feeling the force of the balloon pushing back. That's due to the gases that are in there. So that means that there's energy inside of the balloon because of this pressure volume relationship. Okay? So that's H. But like I said, we're more interested in delta H, the changes in enthalpy. So I'm going to write it this way. Delta H is equal to delta E plus delta PV. All right, so the change, oops, sorry, I forgot the H. I don't know why I said H. So the change in this one is equal to the change in this one plus the change in this one. Does that make sense? Right, like if you were saying what's the change in the number of people in the room, you could say it's equal to the number of people wearing red shirts that came in plus the number of people wearing blue shirts that came in, right? So you add the changes, same thing here. Now, usually when we're dealing with enthalpy, enthalpy is done under a very specific process. It's done when the pressure is constant. That phrase is almost always in any problem that involves enthalpy because it's based on the definition. Enthalpy is a process that we look at when the pressure is constant, meaning that the external pressure is not changing. If it is, then we'll do something else, but we don't need to worry about that for this course. So if the pressure is constant, this is a mathematical phenomenon that I'm not going to go over, but if you have a change in a product, and one of them is actually one of these two things is constant, you can bring it out of the delta. And so it becomes delta H is equal to delta E plus P times delta V. So now you just have to look at the change in the volume. So this one's constant. Okay. And so that's why you'll see that this is a constant pressure. That way you can use this equation. Okay. So now we have a definition, a working definition of enthalpy change. the enthalpy change is the change in the total energy. So how much energy is coming in or out, plus whatever's going on in terms of the pressure and volume. So this tells us that if you've got your gas mixtures, it could be one gas, it doesn't have to be a mixture, it could just be one gas. If you're compressing it, right, so now it's got a smaller volume, there's an energy associated, an energy change associated with that, and that's in this equation right there. But here's the thing. There is also, this term here is actually in here already. Because what we said was delta E is Q plus W, right? We looked at that earlier. But what was W? W was minus P delta V. So this is actually, Q plus minus P delta V. I remember we talked about how I had the minus in there. So if you have Q plus minus P delta V, so that's your delta E. But then to get delta H, you have to add P delta V. What does that tell you? It tells you that delta H is Q plus a minus P delta V. But then we're going to add this to it. Look what happens. Minus P delta V plus P delta V, and you're left with Q. And this is why enthalpy is of such value to us. It's very simple. What this says is the total energy change in any of these processes is merely the amount of heat that went into or out of the system. So if I have gases in this cylinder, energy can go in the form of heat. It can come out in the form of heat. We talked about that in the lecture yesterday, endothermic versus exothermic. But we also said there's work. We can have work of compression, and we can have work of expansion. What this essentially says is that if we consider enthalpy as the difference in energy, we can ignore the whole work stuff. We just need to worry about the heat. And that simplifies it by 50%. It makes the problem half as easy, or half as hard. So now we have this. Delta H equals Q. Now, what's the requirement of this? Constant pressure. It only works if this is a constant pressure. If it's not a constant pressure, we cannot use this, and we have to come back to Q plus W. Okay. So I'm going to put a little P here to indicate that it's a constant pressure. So this is only valid if the pressure is constant. Hopefully that'll help us with this problem. Measurements show that the energy of a mixture of gaseous reactants, so the energy goes down by 374 kilojoules, decreases, that means it's a negative change, right? During a certain chemical reaction at constant pressure. It's also careful monitoring of the volume change. It is determined that negative 150 kilojoules of work is done on the mixture during the reaction. So the question is, calculate the change in enthalpy of the gas mixture during the reaction. So delta H, change in enthalpy. So that's delta H, H2 minus H1. Round your answer to 3 significant figures. Okay. So let me make a little room here, and let's go through it. So let's see what we do. Energy, so that's delta E. We see that in delta E. Decreases by 374. So that's telling us delta E is minus 374. Okay. Furthermore, by careful monitoring the volume change, it's determined that negative 150 kilojoules of work So that's telling us W is equal to minus 150 kilojoules. Okay. And then they want us to determine the change in it. Change in it. So I still H. Well, it's a constant pressure. So that means the delta H is equal to Q, right? Now, what's the relationship between delta E and W? Delta E is Q plus W. So if we want to find an enthalpy change, we have to find heat. To find heat, we can take delta E and W and then calculate heat. So the logic of this problem, the sort of progression is, you use these two values here to figure out this one, and then that one is equal to that. And that gives you your enthalpy change.
Is that E plus or is that E equals?
Oh, thank you. It makes more sense now, right? That was not an equation, right? So let me go over it again. So we're given delta E and W, so we've got these. So the logic is you find this, and then this is equal to that. Right? So these are both Q. So let's see what happens. We want to find Q, so delta E minus W, right? Subtract W from both sides. So that would be negative 374 minus, but it's minus 150, so minus a minus 150. So if you're subtracting a negative, that's like adding, right? So that's really negative 374 plus 150, which is minus 224. And then because it's a constant pressure, that means that this Q that we just calculated is equal to delta H. So it looks like it's negative 224. So overall, the gas lost energy. It lost 224 kilojoules. Why? Well, mainly because the heat, right? I mean, actually, it lost energy in two different ways. Its total loss of energy was 374, but it lost 374 because it lost 150 in terms of work. So that must be expansion. But it also lost 224 in terms of heat, which means it radiated out to the surroundings. So it gave away two different ways. But so two different ways to do this. Okay. Exothermic or endothermic, that's very simple. Since delta H is equal to Q, we use the same convention that we use with heat. If Q is positive, that's endothermic. If it's negative, it's exothermic. Negative means going out. So since it's negative, negative 224, we would say it's exothermic. Okay. So a little tricky. It's a little tricky because you have to kind of just label what everything is. When they say the energy of, they mean delta E. When they say decreases, they mean negative. When they say increases, they mean positive. When they give you the sign, that's obvious. Work is your W. And then they're going to ask you for enthalpy, the enthalpy change, that's going to be equal to Q. So you're really just using this equation right here plus this one. It's exactly the same. They're all pretty much the same. So I thought they might give you one where they give you the heat, give you the work, and then how you figure the energy. But I think they're not going to do that because that was kind of the previous section. Okay. So it's pretty much always the same. Okay, so the main take home from this then is that we have a new term, and it's easy to get these terms mixed up. So let me just say real quickly about them. So the first term is delta E. So that's your total energy. This is referring to how much energy the gas has. Then you've got your Q, which is the heat being transferred into or out of the gases. Then you get your W, this is the mechanical work being done on the gas, or on the gases, or by the gases. Now, if you're at constant pressure, then this becomes useful. So this is at constant pressure. And the reason it's useful is because it's equal to Q. So the change in enthalpy, you can think of that as how much heat went into or out of the system. And that works if you're at constant pressure. Okay, so it's really just different. We will, in chemistry, mainly look at constant pressure situations. So instead of actually looking at the total energy difference, delta E, we'll mainly look at delta H. That will be our primary method of measuring energy transfer. You'll see this symbol quite a bit. We won't go through the other thermodynamic symbols that you maybe have heard of. If you've taken biology, you've probably heard of delta S, where this is entropy. And you maybe have heard of delta G, which is called free energy. So those are important terms too. We just don't cover them in this course. These get covered in the next course, 10, 12 minutes. So we'll tie all these together in the next course. But for this course, we're just going to deal with these four. This is where we get into the chemistry, right? In a sense, what we were just doing is physics and engineering. Now we're going to look at chemistry. If you take a look, this is pretty interesting. We haven't gone through calorimetry. We'll look at that in the next section tomorrow. But what we can do is we can look at a chemical reaction. So here's the balanced equation for a reaction. Now what is this? This is kind of an exotic reaction. It's not something that I see very often. As a solid, so that's sulfur. Sulfur you've seen before. It's like a yellow, powdery solid that burns, and they put it in matches. Smells like it burns, right? This is fluorine, F2. F2 is like pretty uncommon. You don't see that very often. It's pretty dangerous. If you take one of these essays, you have to react with 24 of the F2s, and you get this other material called sulfur hexafluoride, SF6. SF6 is an amazing material. It has all kinds of interesting properties. But one of its properties is a little dangerous in that it absorbs so much infrared radiation that if it gets into the atmosphere, it works as a really powerful global warming compound. So people have to really control how much of it they use. But it has interesting properties. And we'll look at it in terms of its structure when we get to chapter 8. Now, associated with this chemical equation is a delta H here, a value of delta H. Delta H is negative 9672 kilojoules. So see how it's negative? That means it's exothermic. Exothermic reactions are the ones that release heat. Endothermic absorb heat. If you want to use a chemical reaction to release energy that you can use that energy in the form of heat, you want to use exothermic reactions. So this is highly exothermic. There's a lot of energy coming out of it. So this is a process you could use to generate energy. You could, in theory, run an engine off of that. You could heat things with it because it's negative. It's also a pretty large atom. So, but I'm not gonna talk about where that value comes from, we'll look at that in the next section. But it turns out we can run a reaction and actually measure how much energy comes out. That's something we can do. And so for this one, it's been tabulated as negative 9672 kilojoules. So that's a pretty big value, right? In scientific notation, this would be 9.672 times 10 to the 6 joules, right? Kilo is 10 to the 3, 1,000. And then if you move it 3 more places, that gives you 6. So it's a pretty large amount of energy. That's a great amount of energy. Another reaction would be like this, H2 plus O2 to form H2O. This is the combustion of hydrogen. Here, delta H is negative 285.8. So this one's a lot bigger than that. This is like 300. This is like 10,000. That's a lot of energy. Okay, so now the question is, given these reactions, what's delta H going to be equal to? And what I want to draw your attention to is, this is, by the way, called a thermochemical equation. This is called a balanced chemical equation. If you add the delta H and give it, for that equation, it's called a thermochemical equation. So this thermochemical equation is related to these. In fact, if you take a look, SF6, S8, F2. This equation right here is really this one, it's just they've done something to the equation. It's still the same materials, right? Take a look at the second one, S8, F2, SF6, S8, F2, SF6. So all three of these are related to this one right here. The only issue is what have we done to this equation to get these ones? And so let's take a look at this one's actually a little tricky, so I'm gonna not do this first. I'm gonna do this one first. We'll do the second one first. This one's easier. If you take a look at this one, see how it's got S8 as a reactant, F2 is a reactant, and then SF6 is a product. So it's written in the same direction. Same reactants, same products, same states of matter. Everything's the same. The only thing that's different are the coefficients. So this has a coefficient of 1. This has a coefficient of 1/6. This one has a coefficient of 24. This one has a coefficient of 4. This one over here has a coefficient of 8. This one has a coefficient of 4/3. So what happened? What did we do to get this equation from this one? Any ideas? Yeah, divide by 6, exactly, you got it. So if you take 1 and you divide it by 6, you get 1/6. If you take 24 and you divide it by 6, you get 4. If you take 8 and you divide it by 6, you get 8/6, which is 4/3. And that's exactly what you have here. So all they did to get this equation was they took this one and they divided everything by 6. So that's actually nice. They're not going to divide this one by 6 and then divide this one by 4. They're going to divide them all by the same number. Really what they're doing is they're taking this equation and they're multiplying by 1/6. So here's the rule for this. Energy is additive, it's a scalar quantity. So if you have a certain amount of energy in 1 gallon of gasoline, 2 gallons of gasoline would give you twice as much energy. If you have half a gallon of gasoline, you have half as much energy as you have with 1 gallon. If you have 1 battery, you have half as much energy if you have 2 batteries. So what they're doing here is they're really saying, hey, if you have 1 mole, this is how much energy you get out. How much energy would you have if you had 1/6 of a mole? Right, 1 mole over 6. Well, you think about it this way. If I said I have 100 kilojoules for every 1 mole. Every mole you have 100 kilojoules. If I have 2 moles, you would just multiply by 2, right? And that would give you 200 kilojoules. Or suppose I said I have 100 kilojoules per mole. and then I have a half a mole. Well, that would just give you 50 kilojoules, right? 100 times a half is 50. So all you got to do to find what delta H here is whatever they multiplied these reactants by, which was apparently 1/6, you multiply this delta H by the same amount. Okay, so if you multiply these by 6, you multiply this by 6. So we would take negative 9672. Okay. And then you multiply by 1/6. Okay. Same number. So it's 9672. Yeah, negative 1612. Okay. So really what you're saying is you've got 1/6 the amount here that you have over here, so you have 1/6 the energy. So that would be negative 1612. No unit conversions or anything like that. And again, if you know, some of these might be hard, like where to go from 8 to 4/3, what did you have to multiply by? I mean, you could do that algebraically, it's not that hard. But maybe this one's easier. 1 to 1/6, you multiply by 6. Okay. 24 goes down to 4, you gotta divide by 6. So it's the same. So just pick the one that's easiest, and then check it. Take care of it. Okay, so let's take a look at this third one. The third one I want to do next, because again, this one on the top is actually the hardest one. So let's do the third one. The third one, take a look at what they did here. You got 8 SF6. So there's your SF6. Well, wait a minute, SF6 is over here, it's on the far side. So they got it on the wrong side, right? And the S8 also. The S8 used to be over here, now it's on the other side. And then the F2 is on the opposite side. So what they did was this is what we would call, we would say they flipped the equation. They reversed the equation, right? Yeah, you got it, exactly. Energy goes in or out. So if you change the direction of the reaction, you change the sign. So for this one, check, just make sure the coefficients are the same. 8 and 8 is the same. 1 and 1 is the same. 24 and 24 is the same. So they didn't change the coefficients at all. They're all the same. But everything that was a product is now a reactant. So if they flip, in other words, just if you drew the arrow the opposite way and then wrote it from left to right, that's called reversing the equation. That's what happened, they reverse it, and you're exactly right. If you reverse the equation, so if I write ASF6 goes to S8 plus 24F2, if you reverse the equation, you just change the sign. So it becomes positive 9672. Okay, so positive 9672. Isn't that cool? And that kind of makes sense in terms of our discussion of energy. If you're, like when we were talking about work, compressing a gas, W is positive. Expansion of a gas, W is negative. If it's endothermic, that means energy goes in, heat goes in, so it's positive. And if heat goes out, it's exothermic, and that means it's negative. So reversing an equation just changes the sign and makes it positive. Okay. Now, the problem, let's come back to this one. That's an interesting one because apparently what they did was they reversed it. You've got SF6 as a reactant, here it's a product, so they reversed it. They took everything that was a product and made it a reactant, and then they took the reactants and made products, right? So they did reverse it. So what I'm going to do is I'm saying, hey, they reversed it, so let's make it positive 9672. But that's not everything they did there. They did something else too, right? You got it. So what happened was this was an 8, now it's a 16. So they multiplied it by 2, right? So that means you got to multiply by 2. And anything they did to the SF6, they have to multiply the other ones by the same value. Again, you can't multiply one of the materials by 2 and then multiply another material by 3. So if they multiply this one by 2, they also have to multiply this one by 2.
What's the link?
Okay. You want to see it? 4943 M E E T.
There you go. Leave it there.
Yeah. We have a good number. Okay, so 9672 times 2.
1934.
What is it?
1934.
You got a better brain than I. There you go. All right. So again, it's positive, so it's endothermic. Right? So again, the nice thing about these problems, and chemists like things very simple. So the nice thing about this is that we're talking about enthalpy, so enthalpy is heat. So we're not really talking about work, we're just talking about heat. So we can use the same terminology. Positive is endothermic and negative is exothermic. Okay? Does that make sense? What do you think?
No, it makes sense.
It makes sense? Oh, it's easy. Okay. Awesome.
I think the formulas used are easier to talk about because mostly it's bottom this top. Compare the transform for convertible and
Maybe. What's your math level? What's the highest math you take? Okay, so that explains it a little bit. So the more math you have, the easier this stuff gets. Right? So, if we were going to teach this really at the pre-calc level, we would be giving you more complicated functions or descriptions of this. But so yeah, it's mainly because your math level is pretty high. That's good. Yeah, I think it is. Some people have challenge. Some people find it challenging. So it's hard to say. Okay, let's take a look. Calculating the heat of reaction from molar reaction enthalpy and the mass of a reactant. So this is really getting back to what we did in chapter 3. It's like you're actually just thinking about it. It came to fruition. So here's what they're going to do. So again, this is called a thermochemical equation because we're given the value of delta H, so that's the thermo, and then there's your chemical equation. So it's a thermochemical equation. All right. A chemist measures the enthalpy change or the energy change delta H during the following reactions. So they give us the balanced equation, and then they give us delta H. So this is an endothermic process. Okay, so it's absorbing heat, and then they want us to determine, oh, well, here we go. Is it endothermic or exo, right? That's simple. If it's positive, it's endo. So we've got that one already. And then suppose 31.7 grams of ammonia react. Will heat be absorbed or, released or absorbed? That's actually, in a sense, a little tricky question that you don't need to look too deeply into. They're giving you the amount of ammonia here, but the amount doesn't determine whether something is endothermic or exothermic. What determines whether it's endothermic or exothermic is the sign of delta H. So, think of it this way. If you have a match and you strike it, that's exothermic. It produces heat, right? If you have 2 matches, it's still going to be exothermic. Doesn't matter how many matches you have. The chemistry is what's determining whether it's endo or exothermic. So if it's endothermic here, it's still got to be endothermic here. And endothermic means absorbed, right? It means taking in the energy. Endo meaning goes into. So it's still got to be absorbed. So we didn't have to do any calculations there. We just had to look at what the sign was for both of those questions. Now, when we get to the last one, if you said that energy will be, or heat will be released or absorbed in the second part, calculate how much heat will be released or absorbed, and round your answer to 3 significant figures, okay? So now, this is what we're going to do. We're going to use this thermochemical equation And we're going to use this number here, 31.7 grams. And suppose I had rephrased it. Suppose I said 31.7 grams of ammonia decomposes into nitrogen and hydrogen. How many grams of hydrogen will be produced? You would recognize that as a chapter 3 problem, right? You're given the amount of the reactant, how much of the product you would get. This is not that different from that problem. We're given the mass of the reactant, 31.7 grams. So we know the amount of this. Now we're asked to figure out what delta H is. And delta H is connected to this balanced equation, even though it's not a chemical itself, it's an energy change, right? So here's the relationship. Every time 2 moles of this react, we get 160 kilojoules. That's the relationship right there. Okay? This is written with this being a 2 and this being a 160. If we made this a 1, cut it in half, we learned in the previous problem we would cut this in half and this would be 80, right? So the amount of this depends on how much of this is going in. So it's 2 moles of ammonia for every 160 kilojoules. Now we just ask, do we have 2 moles of ammonia? It doesn't look like it. We have 31.7, but it's in grams, so it's not that obvious, right? We don't know how many moles that is. If it was 31.7 moles, we would know that's not 2 moles. So let's figure it out. How many moles is this? 31.7 grams of ammonia. What's the first step in figuring out how many moles of something you have if you're given the grams? Divide by the molar mass, exactly. So the molar mass, we can kind of estimate it. Nitrogen is 14.01. Hydrogen is 1.01. So you have 14.01 plus 3 times 1.01, and that's 17.04. So divide by the molar mass. 1 mole of ammonia is 17.04 grams. Okay. And again, our dimensional analysis, grams of ammonia cancel. And so it looks like it's going to be less than 2 moles, right? If this were 34 divided by 17 would be 2. Right? Question?
Yes, it says you have another meeting in progress. Won't let us join.
It won't let you join?
No, it says you have another meeting in progress.
Okay, I have to look into that.
Okay.
Thank you. Thank you for letting me know.
You're welcome.
Okay, so 17.04. So you get 1.860. Now, let's estimate this. Like I said, if this was 2 moles, it would be 160. It's actually not that far off from 2 moles. It's pretty close to 2 moles. So it's actually, going to be close to 160. So how do we do the final step? What you do is you save this, you write it this way. You say it's 160 for every 2 moles. So 160 kilojoules for every 2 moles. And then multiply that by 1.86 moles. Okay. And then your moles cancel, and then you're going to have your. But don't forget this 2, right? It's not 160 for every 1, it's 160 for every 2. And so 160 over 2 is 80. So 80 times 1.86. It looks like you get about 148.8. Okay. So notice the sign didn't change, it's still positive, it was positive here. So it's going to be positive no matter what. You can't change that. You could change it by reversing the equation. If we reverse this, then it would be negative 160. But if it's actually this reaction, it's got to be positive 160. Okay. Does that make sense?
Yes.
Good. Awesome. I think that's it for that section. That is it. We went through all three. So we did the pressure volume work, understanding the definition of a, well, four, sorry. And then, general properties within that. Okay, so it looks like we're good. That's pretty much the whole section. So tomorrow, what I'll do is I'll start working on the next section, which is calorimetry. And that's the bulk of it. Once we get through 5.4, there's only one more section, and that's just a little bit, a couple problems out of that. So we're doing pretty good today. It's Tuesday. We've got more than halfway through the chapter. We should be good to go on this out. By the way, I have not graded exam 2 yet. I'm going to start going through them. I'll probably start going through them tomorrow afternoon. So if you know, for your exam 2, look at your score, I would say another day or two to see if it got adjusted. And very good. Yeah.
So I emailed you about an issue I had with my exam about how I accidentally started the exam trying to do topics.
Oh, okay.
And I tried to log out to see if that would stay for pause the timer. But I logged out like 15 minutes early and I logged back in and set 48 so it showed that the time was going no matter what. So I was only trying to get like a second thing on it. I tried to try to solve it with just acknowledge and I only got 10%.
Thank you, Professor. Have a good day.
Take care.
You got a second.